final speaker of the day. How's everyone doing? Woo! Woo! 4 people, yeah. We're going to be focusing on our last presenter, who is Brianna Gopaul. She's a 15-year-old quantum computing expert who will chat about its future applications. This summer, she worked as an intern at Xanadu, which she was building a platonic quantum computers to revolutionize how we're approaching the world's toughest problems. And while she was there, she published documentation about CV quantum gates. This is awesome. Please welcome Brianna.
Okay, so I want everybody in the audience to close their eyes. Eyes closed. And on the count of 3, you're going to open your eyes. 1, 2, 3. Now what probably happened is that when you closed your eyes, you saw nothing but darkness. And as you opened your eyes, you started to make sense of the world again as light seeped in. But what if I were to ask you, what is missing from this description? You'd respond with nothing. Because as humans, this is all we can see. In fact, humans perceive what is called the classical world, where things operate in this linear fashion and can be described by classical physics. But if we were to analyze what happened a couple of minutes ago and looked at what happened on a really, really small scale, we would see particles of light called photons. And in other instances, I have to get the clicker. We would see particles of light called photons. And in other instances, neutrons and electrons. And what makes these particles so interesting is that they follow the laws of quantum mechanics. So I can have a photon have a 50% probability of being right beside me and a 50% probability of being all the way across the room. And that sounds bizarre because I can have a 50% probability of being here on stage and a 50% probability of lying on a beach on Cuba. I mean, that would be a sick superpower, but that simply isn't how our world works. And the reasoning as to why these particles can do these weird things is because, as I said before, they follow the laws of quantum mechanics. And for the past couple of decades, scientists have been asking themselves this question: how do we leverage this weirdness of quantum mechanics to create technologies that can then benefit humanity? And one technology that they've come up with is quantum computing. And I've been fortunate enough to be immersed in this space for the past couple of months. For example, in April, I and a couple of TKS students, we went to the world's first quantum computing hackathon at Rigetti. For the past 3 months, I've also been interning at Xanadu, a quantum computing startup in Toronto. And there, they're working on some really insane things. I've also been able to receive mentorship from some of the smartest people in the space on their quantum machine learning team and their quantum algorithm team. And my first project was to create my own piece of documentation that describes how their quantum simulator actually works. But why am I here today talking about this technology? In fact, why should all of you care about it? Well, quantum computing shows the potential to solve some of the world's most difficult problems. And let's just look at 3 problems by example. Cancer, water accessibility, and clean energy. I don't have to show you statistics to prove that these 3 problems are 1, affecting millions of people today, and 2, will continue to affect millions of people if we don't solve these problems soon. So why haven't we been able to solve them? I mean, for the past couple of decades, people have invested hundreds of thousands of dollars into cancer research, and yet our detection, prevention, and treatment efficiencies aren't the greatest. Similarly, for water accessibility, here in Toronto today, we're talking about using technologies like artificial intelligence and blockchain. And yet, up north in northern Canada, there's still Canadians who don't have access to clean and fresh water. That's insane. And with respect to clean energy, with rising global temperatures and sea levels, we're going to see that there's going to be a greater need for an optimized and sustainable source of energy in the next few years. And the reasoning as to why we haven't been able to solve these problems is because they're so complex. They encompass so many variables that if we were to try to give a type of problem like this to a computer, let alone a human brain, we wouldn't be able to understand it because it's so large in size. And so if you've been looking at trends by major tech companies recently, IBM is one of them who has been like who has dedicated a portion of their company towards actually creating quantum computers. Similarly, Microsoft did the same thing, except they took a bit of a different approach to it. But going back to these problems, let's actually try to solve them now. For cancer, we can use a quantum algorithm called Shor's algorithm and a clustering technique to then increase the prevention and detection rates of cancer. For water accessibility, we can compute the solution to the traveling salesman problem, which is a problem that computers have never been able to solve, and compute the solution using quantum annealing, which is just this specific type of architecture for quantum computing. And once we compute the solution, we're going to have the most optimal routes to then deliver water to very remote locations. And for clean energy, we can use specific screening techniques and quantum generative adversarial neural networks and other generative models in machine learning to then generate these very optimized structures to create sustainable sources of energy. But now that we've understood that, one, the classical world operates in a fundamentally different way from how the quantum world works, and two, quantum computers show the potential to solve some of the world's difficult problems, let's actually try to understand how this technology works. So first, when you think about your laptop or any classical computer, it uses binary bits, which can be represented as zeros and ones, whereas a quantum computer uses qubits. And these qubits follow the laws of quantum mechanics, meaning that they can be in superimposed states, or they can be in entangled states. But specifically, the type of architecture that I've been working with at Xanadu is called continuous variable quantum computing. And this is where, instead of qubits, we're using this unit of information called Q-modes. And these Q-modes are really interesting because they're actually pulses of laser light. And each Q-mode can represent a number of varying photons. And so to manipulate these Q-modes, we actually put them through these optical setups, which consist of mirrors and beam splitters, which basically transform the shape of the light. And so when we're talking about, okay, how are we going to program this quantum computer? How are we going to feed instructions to the quantum computer? We're going to use quantum circuits. And these quantum circuits are going to have specific gates, similar to how when we're talking about your laptop, we're going to use circuits and Boolean logic gates. Now we're going to have quantum logic gates. And in this case, you can see above that we've applied a squeezing gate and a measurement operator. And quite literally, what the squeezing gate does in Strawberry Fields, which is Xanadu's software platform, is that it literally squeezes the light on its two axes. And that's just how we've manipulated that form of light. But what gets really interesting is when you have these really complicated gates that seriously use its quantum properties. For example, in the slide above, you can see that we have this really weird transformed shape. And previously on the left side, you could see that it's in its vacuum state, which is where no operations have been made on the Q mode. But on the right side, we applied this, what is called a cubic phase gate. And this gate completely transformed the shape of our light. So that's what we're going to be operating on in continuous variable quantum computing. And later on, we're going to have quantum algorithms. One algorithm that Xanadu is working on in particular is called Gaussian boson sampling. And what they're thinking of for a Gaussian boson sampling is applying it to finance, to compute financial derivatives. And keep in mind that our computers have never been able to do this before. But if you took away anything from this talk today, I want you to remember one thing. For the past couple of decades, we've spent an immense amount of time, energy, and resources into finding the solutions to these problems in the classical world. And what we found is that we haven't been able to find these problems as shown by our three problems: cancer, water accessibility, and clean energy. And the reality is that what we're doing right now with current methods is we're using pails of water to set out what is a forest fire, when what we really need is a water hose. And so today, I implore you guys and everybody in this audience to just really start learning about quantum technologies. And humanity should also shift our focus to looking at the quantum world for the solutions. Because if we really want to solve these problems that have been plaguing humanity for the past couple of years, we're going to have to take a very different approach. Thank you. Oh.
Questions for Brianna? Okay, I'll ask you a question, Brianna.
Great.
So you mentioned IBM is working on a quantum computer for business.
Mm-hmm.
How far away do you think we are from practical cost and applications for sizable businesses?
Yeah, so it really depends on the type of quantum computing architecture that we're talking about. For IBM specifically, they're using superconducting qubits. And I'm not sure how many qubits they have currently, but to really be able to perform the computations that will then impact humanity, for example, solving that traveling salesman problem, we're going to need on the scale of like 1,000 to 2,000 qubits. And currently we're at, I think IBM is at 71. And so with respect to how long it'll take, it's going to take around 5 to 10 years for us to have a practical quantum computer. But that really depends on how much investing and how much attention is going to go into these quantum technologies. And currently, a lot of people don't know about this technology, and a lot of people aren't paying attention to them.
Great, thank you.
Yep.
Sure.
So yeah, one major risk or one potential risk of quantum computing is that it's going to break RSA encryption. And this is completely possible once we have a practical quantum computer. And what that means is that, well, currently there are actually a couple of companies working on post-quantum cryptography. And what that means is that a lot of the architectures and platforms that are reliable currently on RSA encryption will have to change. We're gonna have to have platforms that are going to be adaptable to the new technologies such as quantum. And so, as I said before, people are going to have to start working on post-quantum cryptography, and there's already some companies and research groups who are doing that. Any more questions? Great.